Alright, today we're going to take a look at simplifying trig identities, and these are all going to involve some sort of factoring. If you remember back to Algebra 1 and Algebra 2, some of this stuff should look pretty familiar. Once again, at the top of your papers, I always write the three Pythagorean identities: sine squared x plus cosine squared x equals 1. 1 plus tangent squared x is equal to secant squared x, and 1 plus cotangent squared x is equal to cosecant squared x. Right. So let's take a look at the first example here. We have secant squared x times cosecant squared x minus secant squared x. I mean, if you wanted to, you could probably rewrite this secant squared x as 1 plus tangent squared x, but you're not making the problem any easier. So let's not go that route. If you remember back to Algebra 1 or Algebra 2, when you have the same values in two different terms, keep in mind this is one term, this is another term. Terms are separated by addition and subtraction. If I have the same value in both of those, you can factor them out. So I can take a secant squared x out of here and out of here. Right. If I take a secant squared x out of this part, the first term, I'm left with just a cosecant squared x. And if I take a secant squared x out of a secant squared x, I'm left with just a 1. Right. And now let's look to our Pythagorean identities. Cosecant squared x minus 1, if I bring this 1 over, so we subtract 1, that's the same thing as cotangent squared x. So I can rewrite this as secant squared x times cotangent squared x. Now I can use the reciprocal identity to write this as 1 over cosine squared x, and cotangent, using the quotient identity, is cosine squared x over sine squared x. These will reduce to 1, and I'm left with just 1 over sine squared x, which is the same thing as cosecant squared x. In the second example, I have sine squared beta minus 25 over sine beta plus 5. You definitely can't use the Pythagorean identities there, but in the numerator we have a difference of squares. I can factor that to the sine of beta plus 5 times the sine of beta minus 5. It's the difference of squares, and if you're not sure about your factoring, you can always distribute or FOIL these back through and see if you get back where you started. Sine of beta times sine of beta is sine squared beta. Sine of beta times negative 5 is negative 5 sine beta. This is positive 5 sine beta, so they're going to cancel out. It's going to be 0, and 5 times negative 5 is negative 25. On the bottom we have sine of beta plus 5. Right. This will reduce with this, and we're left with just sine of beta minus 5. In the third example, we could also write this as a difference of squares, or at least the same concept. We could write this as sine squared x plus cosine squared x times sine squared x minus cosine squared x. Keep in mind, our middle terms will cancel out when we FOIL, and sine squared times a sine squared is a sine to the fourth, and cosine squared and cosine squared is negative cosine to the fourth x. Now, Pythagorean identities, this works out nicely. Sine squared x plus cosine squared x is just 1. And here we're left with sine squared x minus cosine squared x. Now, in order for these to be simplified, they need the least number of trig functions. So we could rewrite sine squared x. We could rewrite that as 1 minus cosine squared x. Move this to the right side here. So we can rewrite sine squared x as 1 minus cosine squared x, and then we still have this minus cosine squared x. If I have two of these, I can rewrite it as 1 minus 2 cosine squared x. Right, let's go down to the bottom. Once again, this can be factored. I can factor this into cotangent squared theta plus 1 times cotangent squared theta plus 1. Once again, if you wanted to check it, that's cotangent to the fourth, that's 1 cotangent, that's another one, so there's 2 cotangent squareds, and then 1 times 1 is 1. Cotangent squared theta plus 1 is the same thing as cosecant squared theta, so I can rewrite these as cosecant squared theta times cosecant squared theta. If I'm multiplying, I'm going to add the exponents, so that's the same thing as cosecant to the fourth theta. Right. And the last example here, I don't have anything squared, so I can't use any of the Pythagorean identities. So what I'm going to do is I'm going to rewrite the top, and I'm going to use the quotient identity on tangent. It's going to be the sine of phi plus tangent is sine over cosine, and all that's still over 1 plus secant phi. Alright, now that doesn't look any cleaner than it did before, but something nice happens on the top. I actually have sine in both of these numerators, so I can factor it out. So what I'll do is factor sine out of the top, and I'm left with, if I take a sine out of this first term, I'm left with a 1 over 1, which is just 1. If I take a sine out of the second term, that's just a 1 over cosine, divided by the denominator is going to stay the same, 1 plus secant phi. And now, if I rewrite this 1 over cosine, 1 over cosine is the same as secant. So I can rewrite the sine of phi times 1 plus 1 over cosine is secant divided by 1 plus secant phi. These will reduce, and I'm left with just sine phi.